select a particular, you have to do a lot of hit and try. Still, you say, yes, sir, this functional group is probably, for example, with I have shown you the example of Ricip, that is the जो हम लोग खाते हैं, the omeprazole. The omeprazole is a drug for which it might be determined by some other methods also, but with this one we have selected is from the laboratory an ordinary reagent like 2,4-dinitrophyllanitrazine. Organic labs there are a lot of present in there. We said that, oh, it's a ligand, and if we use carbon disulfide, it can form dithiocarbamates, and thiocarbamates are extremely metal loving ligands. So why don't we hook up this and prepare a dithiocarbamate? When we prepared a dithiocarbamate, we said that let us try with the silver nitro. When we added the silver nitro part, it gives us a particular absorption due to the functionality. Now this the reason why we chose the 2,4-dinitrophenylidrazine, that it has got certain electron withdrawing effect, and the omeprazole that we have got has got electron donating groups like methyl and methoxy groups. So we thought that there might be electrostatic interaction, and this may be determined, and that actually worked. So you have to select. There's a lot of work that you can do with the help of the literature. It's very interesting. It's not. I don't say it is difficult. It is difficult. It's not very difficult, but you have to be very, very consistent.
Thank you, sir. Thank you so much.
Okay.
Thank you, sir. Is there any other question from the audience? Thank you, sir. Thank you so much for your very informative lecture.
Thank you. Thank you, sir.
Our next lecture is by Professor Dr. Nizamat Sari. I will request Professor Farooq Anwar to please introduce Professor Nizamat Sari.
Okay, thank you. Okay, Assalamu alaikum, Prof. I have the honor to introduce you. Professor Nizamat Sari has completed his PhD from Kagoshima University, Japan. He joined Faculty of Food Science and Technology, University Putra, Malaysia in 1996. He has held various positions in university, including Head of Food Science Department, Deputy Dean of Academic and Student Affairs, Deputy Director of Academics, Staff Development, Director for Center of Academic Development, and presently Professor Nizamat Sari is working as Dean, Faculty of Food Science and Technology at University Putra, Malaysia. His expertise is in food enzymology, food biochemistry, biotechnology, food chemistry, functional foods, and food proteins. Professor Nizamat's research work includes the fundamental aspects of food enzymology and their desirable and undesirable implications. This encompasses the applications of food enzymes for the production of food ingredients as well as food with special physiological functions. Especially, he is focusing on functional food and nutrapharmaceutical developments. Current research topics of his research group include purification, characterization, and kinetics of food enzymes, biosynthesis, and production of gamma aminobutyric acid in food systems, enzyme regulations in food systems for the production of high quality foods, production and characterization of proteins and peptides from various food protein sources, and their structure function relationship with respect to their biological functionalities. His special research interests include peptides with antihypertensive, antioxidant, antimicrobial activities. I would like to request Professor Nizamat to please start your presentation. Thank you very much.
I think Professor Nizamid has some connectivity issue. Let me just contact him and let's wait for a minute. I think Professor Nizamid has still some connectivity issues. Let's move to our next speaker. Meanwhile, he sort out the problems. I would like to introduce you about the Professor Dr. Farooq Anwar. Professor Dr. Farooq Anwar, he has done his PhD in analytical chemistry and he has over 20-year research teaching experience in many national and international research institutes. His main focus on the research is on phytochemistry and food chemistry. He has completed his PhD in analytical chemistry from the National Center of Excellence in Analytical Chemistry, Jamshoro. And later on, he earned 2 postdoc fellowships, including one from the University of Lethbridge, Canada, and another from University of Putra, Malaysia. He has served as an associate professor at the Department of Pharmaceutical Chemistry at the Prince Satam bin Abdulaziz University, Saudi Arabia, for a period of 3 years. Presently, Professor Farooq Anwar is serving as a director of Office of Research, Innovation and Commercialization, and as a director, Institute of Chemistry at the University of Sargodha, Pakistan. In addition to involvement in different funded research projects as a principal investigator, he has supervised 11 PhDs and over 60 MPhil research students. He has published 250 publications with an impact factor of more than 350 to his credit. He has 10,000 ISI citations along with 20,000 Google Scholar and 15,000 ResearchGate-based citations. He has been enlisted as a productive scientist of Pakistan by Pakistan Council of Science and Technology, Ministry of Science and Technology, and he has been elected as a Fellow of Chemical Society of Pakistan. Based on his excellent research achievement and contribution, Pakistan Academy of Sciences has awarded him Dr. Ataur Rahman Gold Medal Prize in 2010. Moreover, he has been selected as a TWAS Young Affiliate Fellow by the World Academy of Sciences. Recently, he has been awarded Research Excellence Award 2018 by the Prince Satam bin Abdulaziz University, Saudi Arabia. And last but not the least, he has been enlisted in the top scientists in the world on the basis of the citation and the research contributions. I will request Professor Dr. Farooq Anwar to please start his presentation and valuable talk, please.
Okay, Bismillahir Rahmanir Rahim. The topic I selected is about green extractions in food chemistry with special focus on green extraction of functional components and high value bioactives. Plants, are important source of different types of food and medicine, and they have been used since a long time as a source of food and medicine by the folk people in several civilizations. However, recently, with the revival of interest in the use of plants as a source of food and medicine, there is a revival of interest to use plants and natural components for physiological benefits as well as for the cause of nutrition. Basically, this is the same old concept which was introduced by a Greek philosopher who is known as father of medicine. Let your food be your medicine. Basically, the Japanese, they started a new science, a science of functional food and nutraceutical in 1980s. And the first article which was published in Nature News, Japan explores the boundary between food and medicine. So this was basically the beginning of the modern nutritional science, which is named as optimal nutrition. Plants, are the important source of different types of functional food components and nutraceuticals, and the functional nutraceutical which are derived from fruits and especially vegetables. They have a very significant impact on the principles of nutrition, complementary and alternative medicine. In this slide, you can see some of the very important sources of different types of functional components, including different fruits, spices, herbs, and some medicinal plants. Here you can see a list of some functional components. Basically, the functional components are those components which have some nutraceutical value in addition to some nutritional attributes. And functional foods are basically those foods which, in addition to having some nutritional value, do have some physiological benefits. They can functional components, starting with the carotenoids, which are an important class of antioxidant components present in different vegetables and fruits, especially the alpha carotene, beta carotene, lutein, and lycopene. These are some of the important type of carotene, and they are linked with the reduction of the to reduce the blood cholesterol and other cardiovascular diseases. Essential fatty acids, they are important and mostly present in different vegetable oils, especially flaxseed oil, hemp, and canola are some of the potential sources of omega-6 and omega-3 fatty acids. Among the plant kingdom, flaxseed, which is basically the linseed, they are richest source of omega-3 fatty acid, alpha-linolenic acid. Hemp is another potential source. The hemp seed oil is a rich source of essential fatty acids, and these fatty acids are linked to the risk of cardiovascular diseases. Conjugated linoleic acid is another functional fatty acid, which is present in cheese, meat, and other this type of products. Coming to another very important class of natural antioxidants, which are known as tocols, including both tocopherols and tocotrienols. This type of compounds and delta, they are present in different vegetable oils, and they have antioxidant activity and also impart some health benefits. Phenolic acids are one of the most important class of phytochemicals, secondary metabolites, which have multiple biological activities and also have very strong antioxidant activity. Many fruits, especially the fruits from Rosaceae family, such as apple, pear, berries, small fruits, grapes, cereals, many grains and vegetables are potential source of different types of phenolic acids. Phenolic acids have antioxidant activities and they can reduce the risk of degenerative diseases. Similarly, polyphenols, another class of phenolics which are present in different wine, olives, grapes, chocolates, berries, fruits. They are also important in terms of their multiple biological activities. Isoflavones and similar other flavonoids present in soya, citrus, and citrus byproducts. They are also important to neutralize free radical present in the biological systems and can reduce the risk of certain cancers. Lignans and tannins, this is another class of polyphenols which are highly polymerized products, and they are present in flaxseed, cereals, and some vegetables. Recently, biopeptides are also coming to the forefront, and they are gaining much recognition of researchers due to their multiple antioxidant, antimicrobial, and other important biological activities. Vegetable proteins are, very important source of different types of biopeptides, and recently the food researchers, they are very much interested and focusing on exploration of novel sources of biopeptides, especially plant-based. Recently, there is another very important area where we can explore many functional components, especially the byproducts and agro wastes of fruit processing industry, the peels, the fruits, peels, seeds, and the kernels of different fruits and agricultural products. They are important due to having potential as a rich source of different types of functional components, especially the phenolics. For example, here you can see apple, grapes, citrus, and banana. These fruits are important, and they are especially the peels and other byproducts, waste products, which are derived from fruit agro processing industry. They are being explored for value addition, especially looking into their rich profile of phytochemicals. Similarly, rice kernel, important source of phenolics. Okay, coming to the main topic of today's talk, which is about the extraction of functional and nutraceutical components. Indeed, extraction of bioactives is a challenging task because of several factors, especially, the presence of these compounds. There are diversity of huge reserves of plant sources. There are many plant materials, including the fruits, cereals, grains, which are important source of different types of functional components. These components also vary with regard to their presence these compounds also vary from viewpoint of their biological functionalities, polarities, reactivities, and concentration levels. Their concentration may vary from traces to few milligrams and even up to grams per kg in different materials. Also, extraction efficacy of any method. It also depends upon the nature of extraction solvent and the technique which we are applying for the extraction of these bioactive components. The extraction cycle is also important. In first extractions, mostly amounts are extracted. However, there would be a chance that a significant residual amount may remain in the residues. So we have to go for second-like extractions. Similarly, sample solvent ratio is another important parameter. We have to optimize the distribution, the solid solvent ratio. Normally 1:8, 1:10 is fine. Similarly, the extraction time, the extraction temperature, they are also important attributes, and we have to optimize in most of the cases the extraction parameters. The chemical nature of the plant components is also important. Basically, conventional extractions, which mostly involve like maceration, decoction, infusion, percolation, soft salt extraction, and hydrodistillation. These are some of the common conventional extraction techniques which are being used by the researchers working in different areas. However, these conventional methods have certain limitations with regard to low extraction yield. Some of these methods are tedious and time consuming, as well as some of the methods may involve large volumes of organic solvents. Safety and environmental issues are there, especially due to emission of volatile organic compounds. There is a possible degradation of targeted compounds in some of the methods which involve heat. So there is some option to look into some alternative methods as compared with the conventional extraction. If you see here, some of the conventional methods are given, and which shows you the solvent, the technique, and the time, the limitations. For example, in case of soft salt extraction, we can use some organic solvents like methanol, water even can be used, and in certain cases hexane, and a large volume of the solvent is involved. The temperature, there is a chance in case of soft salt extraction that some of the heat sensitive compounds, they may be destroyed. And if we talk about the maceration, this is fine, but again, you have to store the samples for shaking for a long period, even for 3 to 4 days. And large volume of the solvent is also involved. As far as orbital shaker is concerned, this is quite applicable method and can be used for extraction of a wide array of phytochemicals and high value components. There is no pressure involved. However, the time overnight, 12 to 24 hours may be involved. Okay. Next slide. Next. Okay. So recently there is a greater concern about some alternative methods for extraction. Basically, keeping in view of the principles of green chemistry, which is also known as the sustainable chemistry. Recently, the scientific community, the researchers, they are shifted to some green extractions. And green extraction process basically focuses on new and innovative technologies, process intensification, use of agro-solvents and renewable natural materials, and energy saving, as well as green extractions ensure a safe and high quality end use products. There are 6 basic principles of green extractions. Number 1, we are looking forward for some innovations by selection of new varieties and use of renewable plant resources. Basically, the over-exploitation of natural resources, especially the plant resources, and ill-controlled harvesting is a problem. It is a threat for the preservation of the biodiversity. And there are several examples that some of the plant species, very important, they have been extincted, and due to especially over-exploitation. A typical example is the Taxus species, which are important source of anti-cancer drug, And in 1970s, a huge quantities of the bark of Texas were harvested, and the bioactive components were extracted. Similarly, another very important example is the Artemisia plant, which is a potential source of anti-malarial drugs. So basically, when you are exploiting any species with like ill-controlled harvesting, there would be a danger that these species will be, by the time they will be extincted. Similarly, the green extractions also focus on the use of alternative solvents, especially the biosolvents, which are biodegradable, principally water and agro-solvents such as ethanol. And similarly, we can use fatty acid methyl esters as extraction solvent. We can use different essential oils, terpene oils. We can use glycerol as a green solvent. Green extractions also focus on reduction of the energy consumption by energy recovery. Especially, we can recover the energy, and this energy can be reused. Next. The fourth principle of green extraction is related to the production of co-products instead of waste. Normally, when in the agro-processing industry, a huge quantity of the waste products is produced. So in green extraction, we are focusing on production of co-products rather than waste products, and agro waste materials can be used for value addition through agro refining industry. Also, the focus of green extraction is on the process intensification, where we can optimize, we can intensify the process, and we can reduce the cost, so we can make the methods cost effective. And the ultimate objective of the green extraction is to produce extracts which are contamination free, especially the food industry, functional food industry and nutrapharmaceutical industry. They are looking forward for some pure and natural extracts. So ultimately, green extractions are very much important when we are producing some extract, especially applicable for functional food and nutraceutical applications. Okay. Here I shared a very important review article which is published by Farid Jamaat, a very eminent researcher working in France. He introduced the concept of extraction of natural products and concepts and principles. This is a very valuable review article recently published, and you can look into this article. Similarly, this research group also published another very important article on alternative solvents, especially they focused on green solvents, including the water and supercritical fluids and some other solvents such as terpene oils and fatty acid methyl esters as extraction media instead of using conventional solvents such as methanol and acetone or chloroform, which are toxic and which are not eco-friendly. So basically, in this article, this research group basically focused on biodegradable or green solvents. Here you can see a list of some important emerging green extraction techniques, including the microwave assisted extractions, microwave hydrodiffusion and gravity, ultrasound assisted extractions, enzyme assisted extractions, supercritical fluid extraction. Another very important technique recently developed is pressurized hot water extraction, which is also known as a subcritical water extractions. Another green extraction process is known as a hydrotropic extractions. And at the last but not the least, another very important emerging technique is the plant milking technology. So I would like to have a brief overview of these methods, and we will also include some of our recent research which we are carrying out in our research group. Starting with the microwave assisted extraction, you know, microwave are non-ionic radiations, and they induce molecular motion in materials or solvents, which especially have dipole, and these radiations may facilitate the extraction of bioactive compounds through sample heating. This non-conventional heating system may enhance the penetration of the solvent into the plant material, promoting the solubilization, and thus improves the release of the bioactive compounds from the materials. There are certain advantages of microwave-assisted extractions if we compare with classical extractions. Reduced solvent consumption and thermal gradients, increased extraction yield of bioactive components, and the process is very efficient. It's a fast extraction process. Hardly 30 minutes extraction is enough for the recovery of bioactive compounds. Another green extraction process is the microwave hydrodiffusion and gravity. This is a unique method where there is no involvement of any solvent. It's a new microwave solvent-free extraction technique, which is applicable for the extraction of essential oils, colors, and antioxidant compounds. The material simply is placed in a microwave reactor without adding any solvent or water, and the internal heating of the water within the plant material facilitates and ruptures the plant cell, leading to release and transfer of the essential oils and other coloring components from the inside of the material to the outside of the plant material, and thus can be collected simply by gravity. Here you see ultrasound assisted extraction. This is also an emerging extraction process where we can use ultrasound radiations to facilitate the extraction of bioactive compounds from plant matrix by effective breaking of the cell walls and improving the release and leaching of the bioactive compounds. There are certain advantages of ultrasound assisted extractions over conventional classical extractions. The process is a simple and efficient. It's a cost-effective method. Reduction in time, energy, and use of solvent is involved, and the process can be used with broad range of applications, especially for large range of solvents. Especially, we can extract huge quantities of the extracts for industrial applications. The process of this green extraction is especially suitable for heat-sensitive compounds. Recently, enzymes, especially the pectinases, cellulases, and hemicellulases, so of this method are concerned, you see enzymatic reactions are substrate specific. So definitely we have to optimize the process variables, especially the catalytic properties have to be understood when we are using any enzymes. The mode of mechanism of action of these enzymes has to be studied, and the cost of the enzyme preparation is also important. But when we are using very pure enzymes, then there would be a problem of the cost as well. We have to optimize several other attributes and parameters, especially the temperature, the pH of the process. So these are some of the challenges which have to be further covered when we are shifting to the enzyme-assisted extraction process. Here you can see some of the typical examples of enzymes which we can use for the extraction of different types of functional components. For example, phenolics can be extracted using cellulozymes, and polyphenols we can use pectinolytic enzymes. Catechins can be extracted using pepsins. Similarly, the seed oils, the triglycerides, they can be extracted using different types of carbohydrases and proteases. Here, I would like to share some of our recent research articles where we use aqueous enzymatic oilseed extraction process, basically relative to the Soxhlet extraction. There is some problem in the networking. Anyway, yeah. So here we shared an article which is basically we used aqueous enzymatic process for extraction of oil from sesame seeds, and we used different carbohydrates enzymes such as viscozyme, nathuzyme, and chemzyme. These were the commercial enzyme preparations, and we were able to improve the oil recovery, and as well as we evaluated the quality of the oil, especially the nutritional and nutraceutical value of the oil was quite improved in terms of high recovery of the phenolic components and tocopherols. Similarly, the oxidative stability of the aqueous enzyme extracted oil was quite improved relative to the conventionally extracted oils, which was using. Okay, here another article on the similar aspect. We used aqueous enzymatic process for recovery of oil from sunflower seeds, and we observed recovery of the oil was enhanced, as well as the nutraceutical value, the functional food value of the oil was improved. Similarly, we published several articles. I am skipping some of these. Here, another article you can see here, we used a cold pressing method. Basically, in enzyme-assisted oilseed extraction, there are two aspects, two school of thoughts. One is aqueous enzymatic extractions, and the other is enzyme-assisted cold pressing. So we applied in this article, in this research, we used enzyme-assisted cold pressing method. We pre-treated the seeds with enzymes, and then these enzyme pre-treated seeds were extracted by cold pressing method. And we also compared the quality with the conventionally extracted oils, and the quality of the cold pressed enzyme assisted extracted oil was significantly improved in terms of high recovery of the tocopherol contents and antioxidant properties, as well as oxidative stability. Here another article you can see on the similar aspect. We extracted large quantities of the oil as well as vegetable protein from canola seeds. In this article, we used enzyme-assisted supercritical fluid extraction as an alternative method. And Okay. We are sorry for this situation. Actually, I think it's some technical problem in the networking today, unfortunately. Anyway, we can continue. So supercritical fluid extraction, an important cost-effective process of extraction, which is particularly safe and environment friendly. And this approach, this process avoids thermal degradation of natural compounds, especially we can have a very aesthetic and non-pathogenic extractions. The method is versatile in terms of its applications. We can optimize we can also improve the polarity of the supercritical substances by introducing another co-solvent, which is known as a modifier. Especially we can use ethanol, and we can use supercritical fluid extraction for purification as well as for denicotation purposes. Here you can see a schematic diagram of a supercritical fluid extraction process. Basically, supercritical carbon dioxide is used as a green solvent, and this gaseous carbon dioxide can be converted into supercritical carbon dioxide by exerting certain critical temperature and pressure. When we when we subject gaseous CO2 to supercritical pressure and supercritical temperature of 32 degrees Celsius and about 72 atmospheric pressure, this gaseous carbon dioxide is converted into supercritical cycling process.
जी सर
Connected है?
हाँ जी
Yeah. इसको बोलते हैं। इसको switch off करें। ठीक है ना इसमें? Working?
जी सर आई थिंक जी सर
Are you listening? Please, are you listening, voice?
Yes, sir. We are listening.
Yes,
Okay,
sir,
okay.
we are listening.
Sorry, basically there is some technical problem. It's raining outside and
Yes, sir.
might be some technical issue. Anyway, we are continuing. Here in this table, you can see typical extracted phenolics. You can see the different conditions of temperature, time, and pressure which are applied. Solvents can be used as a modifier, such as ethanol, water, to improve the properties of the carbon dioxide when we are using it as a supercritical carbon dioxide. Basically, there is a problem with the supercritical carbon dioxide because it's not very much polar. And we cannot use supercritical fluid extractions for extraction of polar compounds, especially in normal conditions. However, we can tune, we can optimize different variables, we can improve or we can decrease the supercritical temperature and pressures can be optimized, and we can also use some modifiers, co-solvents, in order to improve the process of extraction when we are using supercritical fluid extraction process. Here, I would like to share another article where we used enzyme-assisted supercritical fluid extraction for the extraction of phenolics from fruit peel, and we were able to extract both hydrolyzable and non-hydrolyzable phenolic compounds effectively. Another recent article, we used enzyme-assisted supercritical fluid extraction. Similarly, some other articles you can see here. Here we optimize the process variables using response surface methodology, which is an important software to optimize the process variables. Another article where we used RSM and ANN to optimize the process extraction variables in enzyme-assisted extraction. In this typical article, we used supercritical fluid extraction to extract oil from basil, which is a supercritical fluid extracted oil has a profile in terms of especially high concentration of bioactive components and the biological activities, including the antioxidant and antimicrobial activities of the supercritical fluid extracted oil were superior as compared with the steam distilled essential oil. Okay, coming to another very important process, which is a recent basically water is a and when we use the water,
Sorry for the disturbance. I think we are back.
Pressurized liquid extraction.
Where we can use
Sorry for
Next.
problems. Let me just. There are a lot of problems.
Pressurized liquid extraction, another process which is known as a hydrotropic extraction. In hydrotropic extraction, basically we can use hydro. Which are able to increase the solubility of water, solubility of the inorganic and organic compounds, especially in water, which are not normally soluble. This method has advantages over classical extraction, very efficient, and we can recover higher extraction yields. Coming to the next recently developed plant milking technology. In this technique, the plants are grown in a greenhouse in a liquid medium known as a hydroponic medium. The plants are not grown in like soil mediums. They are grown in a hydroponic mediums in greenhouses under controlled conditions. And rather than harvesting the plants, we can recover the extractions of the substances through the roots in the culture medium through triggering by physical, chemical, or biological stimulations. This is basically a non-harvesting technique where without harvesting the plants, we can have very specific and very effective extraction of the bioactive components through growing the plants in the culture medium rather than harvesting and destroying the plants. It's a novel non-destructive harvesting technique which yields significantly higher quantities of bioactive compounds, especially applicable for value addition in the pharmaceutical and cosmeceutical products. We can optimize the process variables. We can have high purity and extraction of the bioactive compounds. The process is a renewable and eco-friendly process. Plants are basically preserved. It is also important when we are talking about the biodiversity of the ecosystem. And this technique is especially helpful for biodiversity conservation. Here you can see a few slides where you can see some researchers working in the plant milking technology. And this researcher is basically placing the plant roots in a detergent extraction solution. And another researcher using a resin-based separation technique to extract active components from plant roots in a plant advanced technology greenhouse. Another researcher you can see is putting some detergent solution to improve the extraction efficacy. And this added substance to the hydroponic growth culture increases the permeability of the roots in order to improve the recovery of the bioactive compounds. Similarly, another researcher you can see working in the green extraction process using the plant milking technology. And here the researcher is inspecting a hydroponic crop unit in a monitoring environment. I think the last slide, I can give an overview of the protocol which is used by the phytochemists, especially for the extraction of different types of bioactive compounds. We can have a plant material, and after bringing the plant material into the lab through collection of the samples using a standardized protocol, we can bring the material and we can dry it. For drying, we can have different options. We can use like ambient drying, we can use freeze drying, very important. Some other methods such as sun drying can also be used, because that drying process also affects the recovery of the bioactive compounds from the plant materials. After extraction, we can have crude extracts. These extracts can be evaluated by using different in vitro, in vivo bioassays for different biological activities. And we can also purify these extracts using some liquid extractions or solid phase micro extractions. Especially, we can enrich these extracts for certain bioactive compounds. And then we can go for phytochemicals profiling. We can use some state-of-the-art techniques like HPLC, LCMS, GCMS, or we can use some spectroscopic methods for the characterization of bioactive compounds. So basically, there are two general routes. One is a targeted analysis, the other is a structural elucidation of a novel compound. So in both of these methods, we have to start with the extraction of the plant materials, and we can use different techniques, conventional methods, as well as we can use green extractions and the crude extracts. They will be evaluated, and after evaluation, we can go for chemicals profiling using state-of-the-art analytical methods, including the chromatographic and spectroscopic techniques. So this is an overall methodological process which the researcher can use for extraction and characterization of bioactive compounds. I can conclude my talk in line with the green chemistry principles. Green extraction is a new concept, and this is an emerging area, and green extractions can help to protect both the environment and the consumer's health in terms of recovery and yielding of safer plant extracts for development of healthy nutrapharmaceuticals by adopting innovative and eco-friendly approaches. Meanwhile, it may enhance the competition among industries and the researchers to be more ecological, economic, and innovative. When we are using green extraction process, we are basically saving the environment. So thank you for your patience. Thank you very much. And we are really sorry for interruptions because of some technical issues. And I think it will be smoothly running. Thank you very much.
Thank you so much, Professor Dr. Farooq.
House is open for the questions. Is there any question? Please.
Yes, Dr. Farooq.
Yes, sir.
Yeah, thank you for a very detailed, I think, description of what I have seen in the extraction processes of various plant materials in Pakistan. I am just wondering that Pakistan is so rich in various plants, right from our northern areas till our southern areas, that there are hundreds and thousands of plant species present. What I mean that what are the prospects that why we had not been able to develop so many functional food out of it as much people are making in other countries? What are the prospects that of functional foods in Pakistan using our local varieties of food, of plants?
Thank you, sir. Thank you very much. Yeah, definitely, sir. It's an emerging area, and especially France, they have developed plant milking technology and other green extraction process. They are very much expert. And in Pakistan, as far as our research environment is concerned, some of the research group, they are focusing on green extractions involving like bioethanol or other green solvents. And although there is a huge potential in Pakistan, we have a rich flora, and especially we can develop our own functional food and pharmaceuticals. Recently, some researchers are focusing on especially on moringa. In Pakistan, moringa is becoming an industry, and several researchers and industrial people, they are involved in the development of functional food from moringa. Although there is still room for development using other resources, but moringa is becoming an important industry in Pakistan. Although world over, it is $1 billion industry, especially India and Philippines and European countries. They are working on development of novel products from moringa leaves, especially. In Pakistan, we are producing, and now different farmers, they have started cultivation of moringa on large scale. Even they have like 25 acres, even 50 acres, especially Punjab government and Sindh government and other provinces. They are also focusing on the development of moringa. So definitely, it's very important idea. Basically, there is a need to prompt the researchers as well as the government to give some initiatives to the farmers and especially the rural communities to grow such medicinal plants which may be explored for value addition.
Okay, thank you.
Thank you, sir.
Thank you.
Excuse me, sir, Dr. Farooq Anwar, sir. Myself, Amir Shahzad, your old student in 2012. I'm recently doing PhD chemistry from Institute of Chemistry, Chinese Academy of Sciences. First of all, thank you very much for informative lecture. My question is that in 2 to 3 papers, response surface methodology was used. How can we move from theory to practice for optimization of reaction parameters? Thank you very much.
Yeah. This is a technical question. Yeah, we can use RSM for optimization of different variables, and the trends of computational chemistry. This RSM model is becoming very applicable for optimizing the extraction parameters. Rather than running a series of experiments, we can have a model and we can optimize different variables, conditions, and we can have a optimized protocol, and according to that optimized protocol, we can run experiments and we can look into the yield, extraction yield, and we can also see different biological activities. And even up to the next stage, we can use some molecular docking to study the interaction of the compounds.
Yes.
Yeah. Professor Ahmed is there? He has joined.
Yes.
Okay. I have the honor to introduce our next speaker, Professor Nizam Ansari from Malaysia. Professor Nizam Ansari has completed his PhD from Kagoshima University, Japan. He joined Faculty of Food Science and Technology, University Putra, Malaysia in 1996. He has held various positions in UPM, including Head of Food Science Department, Deputy Dean and of Academics and Student Affairs, Deputy Director of Academic Staff Development, Director of Center for Development, and presently Professor Nizam is working as Dean Faculty of Food Science and Technology at University Putra, Malaysia. His experience in food, biochemistry, biotechnology, food chemistry, functional foods, and as well as food proteins. Professor Nizam's research work includes the fundamental aspects of food enzymology and their desirable
Let me see.
Please, someone can tell him that his mic is turned off.
Can you hear me? Assalamualaikum.
Walaikum assalam. Yes, we can hear you, sir.
Okay.
Okay. Can you see the slide?
Yes, sir.
Yes, right, sir. Okay.
Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Yes, sir.
My dear brothers, Prof. Farouk, Director of ORID, Dr. Fayaz.
Yes, sir.
And I I can see also Prof. Iqbal and all the distinguished speakers. Assalamualaikum warahmatullahi wabarakatuh. And very good afternoon now. I think here in Malaysia is around close to 3 now. Alhamdulillah. I feel really honored today to have this opportunity to be part of the symposium. And I think next time we should also organize together with Sabuada University, at least to you know, at the level of student.
Malaysia, that English boleh jawab ya.
Pardon?
Musliman ni, Malaysia dah.
Okay. Okay. So I have basically I'm very much interested with Dr. Prof. Farouk presentation just now about bioactive compound. And in fact, here in Malaysia, we also we have been working a lot on bioactive compound, in particular Cosmos, a kind of a herbs that we are now basically planting it about 100 acres to produce commercially. But the title of my research today, actually what we are doing currently is plant-based food protein as the sustainable sources from chemistry to application. Try to look into this perspective. Okay, now, why basically UPM is interested in this basically this one in tandem with the Sustainable Development Goal SDG, which has been adopted since 2015 to end poverty, hunger, and protect planet, as well as peace and also prosperity for all. So this basically the purpose basically to transform the world for Sustainable Development Goal to be achieved by 2030. And if you look at out of 17 Sustainable Development Goal and 169 target basically, and SDG number 2, aiming to end hunger, achieve food security, and also improve nutrition and promote sustainable agriculture. And this basically, according to WHO, which define food security, when people have access to sufficient, safe and nutritious food to maintain a healthy and active life. These are among the important factors that contribute basically to the problem, food insecurity, including growing population. Climate change has affected so much, not over in Malaysia, but all over the world. Inefficient agricultural practices. Basically, we are not able to produce enough food. And in fact, Malaysia has been importing a lot of food products from other countries to sustain. And not limited to food waste. And just now, I think Prof. Farouk also was talking about food wasted throughout the supply chain. We wasted a lot of food basically. And of course, if you look at all over the world, there's an increase in global food prices. In fact, in Malaysia now, if you look at the beef, for example, it costs us about 15 US dollar per kg. And that's why in many different countries, basically, people cannot afford to purchase enough food to sustain a healthy diet. And therefore, it is very important that effective action is required, and being a research university in ensuring quality food with affordable prices are available for everyone. So basically, when we talk about food security, these are the concerns. Number one is, of course, about food safety issues, nutrition deficiencies, post-harvest losses, and consumer attitude as well. Yeah, consumer attitude, increasing global population, climate change, and also loss of arable land due to urbanization. So we have a limited land basically for agriculture purposes. There's the reason I think it is very important that it is very critical that continuous need to innovate current food production and technology to meet the demand of increasing food security, sustainability, and also food supply chain. There are few emerging technologies need to be applied to food, which are critical in reversing food insecurity and also in sustaining a constant food supply. Emerging innovation technologies introducing new food items are extremely important with low environmental impact. There's I think into that. So if you look at the one of the main component of food is protein, and to ensure that everyone has access to affordable, high quality protein, which is crucial in meeting the SDG. Yeah, and these are among the current topic that are of interest to all over the world. Cultured protein or cultured meat now. Singapore has just opened a factory producing cultured meat. Mycoprotein, which can be a source of protein. Microalgae, yeah, mushroom, insect. I didn't realize until recently that insect such as cricket is considered halal. Yeah, agro waste, legumes, and these are considered new sources of protein. So if you look at the feed required to produce 1 kg of product, for example, beef requires 25 kg, which is considered a lot. Lamb and mutton, for example, 15 kg. Poultry, 30.3 kg. To produce a kg of meat. Egg, of course, much cheaper, 2.3 kg. But if you look at mycoprotein, for example, such as mushroom, require only 0.55 kilogram to produce a kilo of mycoprotein. So, talking about the global meat demand, which are considered unsustainable, you know, global trend in meat consumption are therefore environmentally unsustainable. So, a transformative shift in global diet are needed, basically. If you look at the environmental impact, animal product emit between 10 to 100 times more GHG than their plant-based counterpart. So if global meat consumption continues as projected, it is expected that by 2050, agriculture alone will take around 90% of the total carbon emission budget required to meet our target of keeping average global warming below 2 degrees Celsius. Yeah. So livestock products are also highly water intensive per kilogram. It's very expensive. Require about 10 times more water than cereal crops. The reason why looking into this, we look into other sources of protein. So I mentioned just now about the few sources of new protein, but what we need now basically innovative technology, tool research need to be developed for their cost-effective production and high yielding, in addition to improvement on their bioavailability. These are very important because not only we are talking about the technology to produce cost-effective protein, but also at the same time we have to look into their bioavailability as well. So this basically my presentation derived from this paper I published recently in Food and Function and Food Research International Food Chemistry, and also recently accepted Innovative Food Science and Emerging Technology regarding protein. So we are basically focusing into pulse and legumes, basically, which are rich in protein. So if you look at the proximate consumption of legumes, basically, a lot of people basically have been working on kidney bean, chickpea, lentil, and all this. But among these, mung bean is one of the best sources of protein. Looking at the proximate combustion of the mung bean, the protein contains 23.86 basically. And when I first started working on mung bean way back in 2015, last year, and China also started working on it. And last year, there's a factory in China producing a protein isolate from mung bean. So they are basically a good source of protein and comparative to other sources. But basically in Malaysia, mung bean, we have been importing mung bean from other countries, I think including Pakistan, from India, from Myanmar. The only thing that is not, mung bean is not being fully utilized because of the phenomenon we call it hard to cook characteristic of the bean, and it is not considered palatable. So if you look at the mung bean, the reason why we are interested in mung bean, of course, it is considered as small green legumes grown on 6 million hectares worldwide. We can find it all over the world, and we can find it abundant in Asian countries, and they are drought tolerant and low input crops. It's considered low input crops, and also the crop produce a low carbon footprint. And these are basically the benefit of mung bean. Not only high protein, but they have also good essential amino acid, and of course, in comparison to soybean, mung bean has a low fat content, and meaning that in terms of protein extraction, it is more efficient and much easier as compared to other bean, because other bean contain quite high fat content as compared to mung bean. So the processing, basically extraction protein is very simple. Basically, of course, there are two techniques. One is dry processing, the other one is wet processing. But more often than not, basically people always use either salt extraction or alkaline extraction technique. These are very common, and commercially people use a lot of alkaline extraction technique. These are basically showing salt extraction technique using sodium chloride, and after that precipitation, and we get the isolate. In the case of alkaline extraction, of course we use alkaline. Normally we adjust at pH 8.0 to 9.0, in alkaline solution, and under this condition, basically protein solubility is maximum, in alkaline condition, and after that it is followed by precipitation to get the protein, and after that involve a drying. It's very simple technique basically. So in terms of techno-functional properties of protein, it is very important that basically to understand the behavior of the protein before we can apply into other food system. So these are from the chemistry point of view. This is very important. For example, ability to absorb water, or we call it protein hydration. In terms of solubility, interfacial properties, which include emulsifying properties, and also stability, and flavor binding ability to bind flavors, viscosity, and also gelation. So knowing these properties is very important, as this will dictate or determine the suitability of the protein to be applied into different food system. Apart from protein, basically protein, we can also produce peptide. Prof. Farouk mentioned about biopeptide, basically. So from mung bean we can produce biopeptide, but the only things that mung bean contain storage protein. It is not structural protein. So if you compare structural protein and also storage protein, they give different properties, basically. But for storage protein, a lot of research have shown that basically they have this property: antimicrobial activity, antioxidant activity, immunomodulatory, anti-thrombotic peptide, anti-tumor, antiviral activity, anti-fungal activity, anti-hypertension. Basically, we have been doing a lot about anti-hypertension, anti-hypertensive activity, antimicrobial. Why we are interested basically in anti-hypertensive? Because we have a lot of problem basically with this hypertension. We are always under stress basically, and one more under pandemic. So basically, we are been working a lot on this anti-hypertensive activity, and anti-microbial activity also not only to human, but also it is applicable also to food system. Say, for example, we want to preserve food. So instead of using synthetic chemical, we can replace the synthetic chemical with this peptide. So we also published a few papers on the possibility of using peptide from plant protein to be used as preservative in prolonging the shelf life of those products. And similarly, antioxidant, it function both to human and as well as to food system. And currently, focus has been also into immunomodulatory effect, which is very important, basically ability of peptide to improve immune system. Okay, the focus of our basically this is to convert it into a texturized vegetable protein. If you look at basically all this one, commercially texturized vegetable protein has been basically is derived from soybean protein basically. So, but none basically from other sources. There's a reason why we choose mung bean protein to be converted into texturized vegetable protein to substitute. It is considered as a substitute to meat in food system, and if it is done properly, it can resemble also meat properties, right? When we can consider this as alternative to animal-based protein, texturized vegetable protein. But currently, texturized vegetable protein has been used in various products, including burgers and all this, yeah, having good properties. This is basically from mung bean. So we extracted the protein, and we call it mung bean protein isolate. And basically, to look into this, to what extent basically it is similar to soybean protein. So we compare with soybean protein isolate, and we look at all the properties, including the techno-functional properties, which are very important basically, as well as thermal properties. And these are the properties. If you look at the protein content, and of course, soybean protein contain a lot of fat basically, and it is basically converted to soybean isolate only after removing the fat. In the case of mung bean protein, because the fat content is very low, so it is not necessary very low. It is not necessary basically to remove the fat. So we can use as it is basically, and from there we just extract protein from mung bean protein and convert into a mung bean protein isolate as compared to this one. This one require, because fat content is very high, at more than 20%, then it has to be defected before being subjected to protein extraction. So in terms of property, basically it is comparable, yeah, in terms of protein solubility, good protein solubility, and comparable to soybean. And this one in terms of water absorption capacity, yeah, and also oil absorption capacity, also similar to soybean protein isolate. But of course, emulsion activity and also emulsion stability slightly lower. Gel foam capacity, basically, it is considered as MBPI was in fact higher compared to SPI. Yeah? But after 30 minutes standing time, there was no significant difference in terms of foam stability between these two after 30 minutes. So, and in terms of ability to form basically, so if basically this is able to form gel, so we can produce a lot more product, gelation base, which involve gelation base. Yeah. So if you look at the mung bean, the requirement to form gel is even lower, yeah, lower compared to soybean. So they require only 12% as compared to 40% for soybean isolate. Yeah. Even though the protein is slightly lower than this soybean protein isolate. These are the more properties basically, yeah. A low denaturation enthalpy compared to SPI, yeah. So meaning they are more flexible in terms of structure. Yeah? So as a conclusion, if you look at the mung bean protein isolate in terms of techno-functional properties, they are basically comparable in terms of solubility, water binding, and all that basically. But mung bean protein isolate are superior in terms of gelling capacity, yeah, and also slightly better in terms of than SPI. better in terms of gelling capacity and also foam capacity. Yeah, and comparatively, if you look at the natural enthalpy, basically this reflects less compared to SPI. So much easier if you want to turn into other product, such as mid analog later on. These are the next. Basically, we look at the effect of drying technique, because it is very important. It is very important step basically before we can turn into product. Currently, the protein product is used for in different form. Basically, it can be used in shake, for example. It can be used in meat product, for example. It can be used to form different product. So that's the reason why drying is very important. So here we look at the effect of drying technique on the physical-chemical properties, techno-functional property, thermal, structural, and rheological. So basically, a lot of chemistry basically look into that. But this one, what we did was basically we produce using pilot scale reactor to extract the protein. Starting with 10 kg mung bean flour, and we extracted the protein. And after that, subject and the protein are subjected to different drying technique, which include freeze drying, spray drying, and oven drying. Of course, a lot of people question basically why do we use freeze drying, but basically freeze drying is very important because we consider freeze drying as a benchmark. Basically, if we want to turn into other product, so we have to look at the freeze drying, the properties of a protein after being subjected to freeze drying, because normally freeze drying give superior quality as compared to spray drying and oven drying in terms of techno-functional properties. So these are basically the analysis that were basically looked into. And then if you look at the protein content, basically freeze drying, of course, maintain high protein content as compared to spray drying, also oven drying. Basically, the protein content are slightly lower as compared to this one. So, this could be due to some protein being denatured during the process, because normally oven drying will take a longer time as compared to freeze drying, to get it dry, as well as spray drying. Basically, also very fast, but it reduces the protein content. We published basically this data in Food Research International. The color, of course, a bit dark. So we treatment basically to kill all the enzymes that are present during the process. You look at the color L value, it's a brown color basically. We do not want to use any other like metabisulfite and all this to basically inhibit the enzyme activities that cause a browning of the flour, of the protein. This basically there's a comparison in terms of the micrograph, scanning electron micrograph of the structure. So in terms of protein solubility, there are of course unity that's slightly different. This one stands for freeze drying. Basically freeze drying give better solubility, very sharp here in terms of solubility as compared to the other two, spray drying and also oven drying. This basically water absorption capacity and oil absorption capacity, and also emulsion capacity, some differences, in terms of the data. And also look at the freeze drying. So see the freeze drying give the LGC. LGC stands for least gelation concentration, require lower percentage to form gel as compared to oven drying, also slightly lower than spray drying. These are the thermal properties of the sample comparison between freeze drying, spray drying, also oven drying. So basically, it showed high TD compared to other plant protein, yeah, in comparison. And this is basically different technique basically used. Did not really affect basically the integrity of the protein. So the protein remain the same, yeah, after being subjected to different drying technique. This basically looking into to what extent basically the protein has been denatured. So looking into the surface hydrophobicity of the protein. We compare also different surface hydrophobicity for different treatment. And this basically FTR result. And also we compare in terms of secondary structure composition to look at to what extent basically the treatment has changed basically the secondary structure. And if you look at this freeze drying, basically it shows comparatively low alpha helix and also high random coil. Basically, meaning that the protein has undergone unfolding, basically. And as if you compare with SD, basically showed very high beta plateau sheet. This is an indication of protein aggregation and ordered structure during the drying process. And for the optical, for this oven drying, you notice that protein aggregation. So basically, because of this, different drying technique will give different characteristic of the protein. So this is basically dynamic logical characteristic of the different drying technique. So as if you look at the freeze drying mung bean protein, it gives porous structure, better gel basically, which it is indication of its elasticity and high protein solubility, and water and oil absorption capacity also very high. And after freeze drying, we notice that there's increased amount of random coil and plus comparatively low amount of beta plateau. This basically good for gastrointestinal digestibility. So meaning that this will increase digestibility of the bioavailability of the product. So in looking at these parameters coupled with techno-functional properties, so freeze drying basically is ideal for the production of meat extended or meat analog. Yeah? And whereas for spray drying, basically we notice that they have a wrinkle structure, better gel of course, but and smaller particle size and high emulsion activity and also stability, which is suitable for meat emulsion. Yeah, for example, meatloaf, bologna, or sausages. Whereas for this oven dry, basically is appropriate as general protein base. But of course, basically, as I mentioned earlier, freeze drying is basically considered a very expensive technology to produce dry powder protein. But as much as we have to basically manipulate the condition of these two techniques, which are much cheaper to achieve the desirable effect as given by freeze drying technique. So basically, this one look into the we look at the effect. Then the protein basically was subjected to extrusion technique to produce texturized mung bean protein, and we look at the effect of moisture basically from 30 to 60%. And unfortunately, we use only single screw because we don't have a double screw. And double screw extruders basically very expensive. If you want to produce a meat analog, basically we have to use a double screw, twin screw, we call it extruder. But unfortunately, we don't have currently. That we are in the process of buying a new one. That will cost us quite expensive, about $400,000 basically to get such equipment. Yeah, but with this equipment, we try to produce mung bean protein and using SRM, RSM basically, and these are the results of the RSM. Then we look at also in terms of expansion ratio, bulk density, rehydration ratio, water absorption index, as well as degree of texturization. Yeah, and finally, we managed to to optimize the method. So basically, to serve as a benchmark, they provide insight on the optimal range for the production of texturized vegetable protein. Yeah. So so this one basically we look at the to evaluate the extrusion that induce the extrusion induce changes on the structural and logical properties of the texturized membrane protein. Yeah, we do the analysis of the structure being produced after being subjected to extrusion process. Yeah, so we look at the moisture content. Moisture content is very important. This basically influence the final product. So we look at moisture content at 30, 49, 43, and 60%. Yeah. At a fixed screw speed, 80.66 RPM. So this is basically the structure we obtain basically in terms of the protein basically, and this is basically the control. A is the control, and this one is the texturized membrane protein. 30%, yeah? And texturized membrane protein 60%. And C is 49.3% basically. So this basically protein in terms of protein solubility of the product. So if you look at this one, the highest protein solubility is recorded at 49.74, yeah, percent moisture. And we also measured the thermal properties of membrane protein, yeah, in terms of the parameter thermal properties of the DNA. Yeah. And we measure also a surface hydrophobicity of the texturized protein, and also several structural properties. Basically, this one to look into to what extent basically the protein has polymerized. Yeah, and this is basically the structure changes using band material intensity in CD reflecting the structure changes and flexibility in texturized membrane protein. This one basically we conducted in India because we did not have the could not measure in Malaysia, so we sent our sample to India to look into the profile of this Fourier safe deconverted curve-fitted spectra, yeah, in terms of secondary structure composition of membrane protein isolate, and so in comparison to textured membrane protein isolate. This one is the secondary structure composition. It shows a different composition of secondary composition of membrane protein isolate, and also textured membrane protein isolate. And we also measured in terms of logical properties of the protein isolate of the membrane, of the textured membrane protein isolate. Yeah, some data that we have collected basically. So if you look at the conclusion here, basically textured membrane protein basically produced at 49.30 feet moisture content should desirable quality, and basically at par with the one that is commercially produced and commercialized in the market now. Yeah. Whereas texturized mung-bean protein produced at 30 and 60, feed moisture content cause a complete protein degeneration and large aggregate formation, which is not needed basically. So we just need basically partial degeneration, which is very important. Yeah. So if protein is completely denatured, what happen is that it will not give desirable properties. So in many instances, partial dilution is more than sufficient to produce dilution, to have good emulsifying capacity, to have other properties, solubility and all this. We just need partial degeneration. And if the protein undergo complete degeneration, then that will affect basically all the techno-functional properties. That's the reason that we found that feed moisture at 49, 43 cause only partial degeneration. The reason why we have to look at it really at the structure level, internal and secondary structure, the polymerization process, and so the and also the fundamental aspect of the product itself. Yeah. So all the parameters basically to evaluate to what extent basically after the extrusion process the structure has changed, and especially you want to know to what extent basically the protein has been denatured. And finally, after the extrusion process, we also look at into the viability, because we know that bean contain a lot of other undesirable material. These are including, if you look at this one, for example, tryptic inhibitory activity, pectic acid, tannin content, for example. These are basically, we call it anti-nutritional properties. And apart from that, we want to know also whether if it, in terms of acidity and also protein quality. Yeah, these are the parameters that we measure in terms of protein quality. Of course, we measure again the techno-functional properties. Yeah, then as I mentioned earlier, more or less the same. But the only things that we notice that these all anti-nutritional properties reduce substantially after being subjected to extrusion process. And this the in terms of protein quality, we measure also protein quality, and we compare with casein diet. Yeah, and these are some biochemical analysis. And this is basically done. Basically, this one done in vitro, yeah, using rat. And after there's no toxic at all. Basically, if you look at the anatomy of heart, liver, kidney, lung, and also the testes. But one thing we noticed that after subjected to extrusion process, basically the viability of the protein improved so much, as indicated by the data. So as a conclusion, basically texturized mung-bean protein should improve techno-functional properties compared to other native and extruded protein. Basically, it gives a superior product as compared to other protein. And extrusion significantly reduce all these anti-nutritional factors like tryptic inhibitors, pectic acid, tannin content, and also, and this is, it was done basically in vivo, exhibited good protein quality in terms of true digestibility, net protein utilization, and also biological values. And basically, toxicity study revealed non-toxic status of the texturized mung-bean protein. So, as a general, as a general conclusion, basically, mung-bean protein has a lot of potential, basically, as a new source of protein to be used, especially in to be consumed in our daily life. I think. Then we are basically looking into this one to keep to develop into we call it meat analog. Is our next basically research work, and also But of course, we need this equipment, we call it. This one is a twin screw extruder, basically. Then this will cost basically about 400,000, you know, to turn into mid and long. This a bit, you know, more or less, I discussed about our funding. Basically, very unfortunate because, you know, I got only one day to prepare all this slide. So I just brief you basically what we have covered basically. And from this work, basically, we have produced four papers in food chemistry, in food research international, and also emerging innovation and emerging technology, and also in food and function, basically. So with that, I thank the organizer for inviting me again to be part of this symposium. Thank you.
Thank you so much. I think there was a sound issue, Professor Nizamit. Can you hear me?
Yeah, I can hear you clearly.
Thank you so much. Is there any question from the audience? House is open for the questions.
So that's the what I basically, this is from the chemistry point of view, they will translate into application of the product. But I wish basically to have more collaboration with my brothers in Pakistan. If you are also interested, you know, working on protein.
Yeah, that was very informative and very good talk, especially as I am a biochemist, and that was very informative to me actually. And Professor, I have a question that on STS page, we have seen the aggregates of this protein.
Mm-hmm.
How you think that how stable it is at the higher temperatures and the other pH conditions?
Basically, of course, you know, it depends on the protein itself. But mung bean is considered stable, yeah, and you know, but what is important basically, of course, when we do the treatment, when it turn into texturized vegetable protein, we need basically only partial denaturation. We do not want to have a complete denaturation. That's the reason why basically moisture content is very important in controlling the denaturation process. And if you look at STS space, basically, you know, in terms of the band, basically the integrity is still there. Protein integrity. Looking at the number of subunit, you know, that was the question basically raised by Food Research International when we submitted our paper to Food Research International. So you are basically at par with the reviewers asking the same question. Thank you.
Yeah, thank you so much. Is there any other question from the audience? Professor, I have another question because it looks very interesting to me actually. And is there any possibility that we just take only a part of the proteins and not the whole protein and use it for the different purposes like the biological activities and other things, like the planticins especially? As you know, the planticins, the plant peptides, they are very active. Mm-hmm. And can we use this mung bean protein in which a special code?
Especially for what? 25 years? I could not hear you clearly, Dr. Fayaz.
I think there was some connectivity issues.
Yeah,
Professor, I was just talking about that. Is there any specific core region present in this mung bean protein which we can just take and we can use that as the peptides we are using from the plants, like the planticins? They are very small in size and we use them for the different biological activities. Is there any core region in this mung bean proteins, or we have to use the whole protein?
Instead of you're asking about the only portion of the protein instead of using the whole protein, right?
Yeah.
No, basically from the food science perspective, basically we want to use the whole protein basically that we want to use as a substitute to meat. That's why the reason why we want to use the whole protein, as a meat substitute. Yeah, but in terms of you're talking about in terms of
thank you so much. Thank you so much, Professor Nizamit. Thanks so much for such an informative talk. Let's move to our next speaker. Our next speaker is Dr. Pratik Sharma. Let me just introduce Pratik Sharma. Dr. Pratik Sharma. Dr. Pratik Sharma, he has studied the genetic engineering at SRM University, India, and he did his undergraduation research project at the National Center for Biological Sciences, NCBS. And after his undergraduation, Pratik moved to the University of Jena, Germany, to do his MSc and MSc Molecular Life Sciences, and then he did his research work at the Max Planck Institute of the Chemical Ecology. Pratik joined the Granger Lab at the University of Birmingham. He joined the lab at the University of Birmingham in 2013 to do his PhD, and he was funded by the Darwin Trust of Edinburgh. Currently, he is working at the University of Birmingham, and his work focuses on multiple antibiotic resistance. His work is funded by BBSRC and the Wellcome Trust. Can I request Dr. Pratik Sharma to please start his talk?
Hi, Fayaz.
Just turn off the mic, please. Hello, Pratik. I think you are here.
Yeah, just a second. I'll start my screen sharing.
Yeah, sure.
Can you see my screen?
Yeah, sure.
Yeah, hi. And thanks for the invitation, actually. And it's quite early for me. I just woke up basically. So, but anyway, we'll start with the talk actually, or should I wait for something?
No, I think you should start the talk. It's fine.
Fayaz, I can hear some echo actually on the background. I'm not sure if it's the real one.
I think it will be fine now.
Okay.
You can start the talk now.
Okay, that's brilliant. Okay, so I'm Pratik Sharma. I'm from the Granger Lab, and today I'm going to talk about the MAR system in ETAC. So MAR system is so called because it mediates the multiple antibiotic resistance. I'm going to talk about this system in ETAC, but actually MAR system has got homologs in all sorts of bacteria, whether gram-negative and possibly also in gram-positive. So before going any further, I would like to give you a brief outline to my talk. So first, I'll introduce you the MAR-RAB operon that encodes a transcriptional activator, MAR-A. Second, I'll tell you about the new targets that we found out by a method known as ChIP-seq. In particular, I'll be talking to you today about AXS-A and MLA-FEDCB. And finally, I will show you some novel mechanisms of resistance to quinolones and tetracyclines. Okay, so first I'll introduce to the MAR-RAB system. So MAR-RAB, which is the multiple antibiotic resistance operon, consists of 3 genes. The first gene in the system is MAR-R. It codes for repressor protein. The second gene in the system is MAR-A, that codes for activator protein, which is a transcriptional activator. And third gene in the system is MAR-B, codes for MAR-B protein, whose function is poorly defined. Together, these form operon. However, in the wild type situation, this operon is poorly expressed. It's because of the first gene in the system, MAR-R, that actually represses the transcription of the operon. And because of that, MAR-A and MAR-B is not produced. So we often get bacteria that revolve multiple antibiotic resistance. So they would have done so by getting mutation in MAR-R the gene or MAR binding site. And because of that, and the repression gets relieved, and hence MAR-A and MAR-B is produced. So once MAR-A is produced, MAR-A upregulates the expression of certain genes like TOL-C, ACRAB, ZWF, but there are many unknown targets. So together, these all give you multiple antibiotic resistance. For a long time, people would have thought actually that MAR system gives you resistance. It's just because of the TOL-C and ACRAB system, because it codes for an efflux pump. So I'll start with showing you the known mechanism of resistance that was ACRAB TOL-C. After that, I'll show you that this is just not the mechanism that is only available right now, but there are a lot more targets actually for this particular mechanism. So now, this is a known mechanism, ACRAB TOL-C. So here's the cell, and this is the MAR-R system. So MAR-R has got mutation in it to get a multiple antibiotic resistance, and hence MAR-A is produced. So this MAR-A targets these two genes actually, ACRAB TOL-C, and they upregulates the expression of efflux pumps. So if you give antibiotics to the cells, and this antibiotics, when they are inside the cell, they can easily be pumped out by the efflux pump. So this is the known mechanism of MAR system, that MAR-A actually activates these genes, results in efflux pump. So if you give any antibiotics to the cells, it can easily be pumped out. Now I will show you that there are many more targets actually which can give you more resistance and a more mechanism of resistance. So how did we find out targets, the new targets for MAR-A? It was a very big challenge to find out targets for MAR-A, because we can find out targets by many techniques like bioinformatics, but that's not easy for MAR-A because it has got quite degenerate targets. And we can do transcriptomics. Again, that's not easy for MAR-A, because if you knock out MAR-A, the effects are pleiotropic. And finally, the obvious answer was to find out by ChIP-seq. For those of you who don't know what ChIP-seq is a way we can measure the binding of MAR-A or any transcription factor on the whole genome. So you can find the binding sites of that particular transcription factor on the whole genome. So this is I've done in ETAC, which is a type of E. coli, and this particular strain of E. coli is called S10407. And this particular strain has got 4 extra plasmids. So in this map, you can see here in the blue, it's the reverse and the forward strand genes, and the green is the MAR-A binding data. Orange is the RNA polymerase binding data. And all the peaks actually, which you can see here, denotes the binding sites. So what we did actually, we have taken the DNA sequence underneath each of the peak actually, and then we found out a conserved motif. So we aligned them all together to find a conserved motif. So the motif which we found was this here. This we call it as MAR box, because this is the only place where MAR-A will bind. So you can also refer it as MAR-A binding site. So this motif is completely resembling the motif which was generated from the known MAR-A binding site, which were like ACRAB, TOL-C, ZWF. These 3 were the known MAR-A targets. So if you look on them, you can clearly see that they both resemble each other, which is a very good indication that our ChIP-seq have worked. So now we have 33 MAR-A binding targets, but we don't know what they do. But in that sense, we were very lucky because we have got Carol Gross's lab data from the US of phenotypic analysis of KO collection. So what she has done is she has taken many different knockouts, not many, the whole KO library actually, and they have grown in many different conditions. To be honest, 400 different conditions, and they measured sensitivity. So from that data, we have only looked on our 33 MARE binding targets, and they calculated from that data, we have just seen and generated a heat map of those sensitivity, which they measured basically. So the heat map looks like this. So here on the left, each square is the different MARE binding site. On the top, we have labeled the antibiotics according to the function they target. And this is all actually the knockout data. So if you get, so for example, to be in here, to simply explain, each colored square in this data is how sensitive or not the knockout of these particular genes are to these antibiotics. So for example, if you knock out TOL-C, you can see that it becomes red across the whole profile, which means it's becoming sensitive across the whole profile of the antibiotics. However, I'm interested in XSEA and MLAF. So XSEA, when you knock out XSEA, they get sensitive to quinolones. So more interesting is the fact actually that quinolones, when they act on the cells, they generate DNA breaks. And XSEA is able to repair them because XSEA is actually coding for an exonuclease 7, the largest subunit of exonuclease 7, and which helps in DNA repair. And MLAF, when you knock out MLAF, they get sensitive to tetracyclines, and it has functions in lipid trafficking. So I'll start with the first hypothesis that XSEA, and this is the XSEA locus. So what happens in here is what we think happens, that MARE actually binds on the MARE site, which is the MAR box, activates XSEA, and results in the larger subunit of exonuclease 7, and which in turn will help them to help them in the DNA repair. So what happens? So when you give quinolones to the cells, and they might generate DNA breaks. So there might be DNA damage in the cells. So when the exonuclease 7 is expressed, it can easily repair them. So let's start with the first part of the hypothesis where MARE actually binds and expresses XSEA. So to prove that, I'll first show you how MARE is actually associated with the XSEA locus. So this is how it's associated. You can see this is the XSEA gene, and the MARE peak is here, which means there is the MAR box, and MARE is binding at the same time as RNA polymerase, which is a very good indication that the MARE is actually activating and the XSEA gene. So it only suggests, but we need to test it out. So for testing it, we have generated 2 fragments. One of the fragment has the MAR box intact, and another fragment, we deleted the MAR box. So now we have taken these 2 fragments and did some binding assays, so some gel sheets assays. So here, you can see in figure A that when you have MAR box intact, which is which was the green peak area, then if you titrate MARE in this direction, you can clearly see that MARE DNA start to form a complex. However, when you get rid of MAR box, you can see when you titrate MARE, you don't see any complex forming in there. So which proves actually that MARE actually binds to the XSEA locus. Now move on to the next part of the hypothesis, that MARE actually activates XSEA locus. So we have again taken these 2 fragments with MAR box intact and a deleted MAR box version and cloned them upstream of a reporter plasmid and known as PRW50, and we have done some beta-galactosidase assays with them. So here's the result for that. So because we measure promoter activity, so you can see when the MAR box is intact, the promoter is quite active. And when we delete the MAR box, the promoters become inactive, which again suggests that MARE actually activates this XSEA promoter. So I have shown you that MARE binds and expresses XSEA but we don't know the functional aspects of XSEA. So I'll show you in the next data that how it actually supports the XSEA gene, supports the growth. So when in the presence of quinolones, which I'll use ciprofloxacin as a type of quinolone. So we did some genetic complementation. So we have used a plasmid, PBR322, which is a medium copy number plasmid, and to overexpress XSEA. So in the first part of the data, I'll show you the normal, the wild type growth actually. So wild type growth of just the wild type cells and the XSEA knockout. So when you don't have any plasmid, so in the sense I have not given any PRW50 in it, sorry, PBR322 in it. And all the cells have been grown in presence and absence of ciprofloxacin. So in the solid green line, you will see is the wild type cells, and in the dashed line, you will see all the data in as XSEA knockout. So when you don't have ciprofloxacin, this is all in no plasmid at all. So when you don't have ciprofloxacin, both the wild type and the XSEA knockout are able to grow fine. However, when you add ciprofloxacin, which is again a type of quinolone, results in DNA breaks, and you can see that the knockout actually becomes really sensitive. So there's a major growth defect. However, the wild type doesn't seem to have that much effect. Now, as a part of a control, I have given just empty PBR322 as to just check that the PBR322 is not interfering with any of the growth in these cells. So you can clearly see again here that they completely resembles like the wild type situation over here. And when you have ciprofloxacin, there's again a growth defect. So now the final part, what I have done actually is I have cloned XSEA gene into this plasmid. And so I've used PBR322 encoded, which encodes XSEA. So in again, this data actually, in the absence of ciprofloxacin, the wild type and the XSEA knockout behaves the same. But when you add XSEA and you grow them in presence of ciprofloxacin, you can see that the DNA in the cells starts growing, which suggests actually that this, because there's a major change from this slide to this part of data and this part. So which suggests actually that XSEA is able to repair those DNA breaks which were generated by ciprofloxacin. So which again proves a little actually that the XSEA is able to repair the DNA when ciprofloxacin have generated some DNA breaks. So and now I wanted to show you that this XSEA gene, because it has got Marbox, and that's why MARE was binding. So we wanted to see that this effect is crucially dependent on Marbox. So what we have done, we have deleted the Marbox on the gene and tried again the growth assays. So in here, in the solid bar, it's the Marbox when the Marbox is intact, and the open bar or the dashed line shows when the Marbox is deleted. So in the absence of ciprofloxacin, both of them with the Marbox or without the Marbox nearly grow the same. However, when you add ciprofloxacin, you can see that in the cells only with the Marbox intact are able to repair the DNA. However, when you delete the Marbox, they again have a major growth defect, which suggests that Marbox is actually important for this complementation. So we have covered the DNA repair part, but we wanted to know what is the actual function of this enzyme is, and this how the domain organization works, and can we have any interference with any of the domain if we mutate any domain actually in this enzyme? Is there any interference between in doing the function, basically the DNA repair? So the domain organization of XSEA looks like this. So it has 4 domains: the OB fold domain, which is responsible for DNA binding; the catalytic domain, which is responsible for the DNA and the catalysis of the XSEA function, basically, so the catalytic reaction of the enzyme, and the coils domain, which is responsible for binding the smaller subunit of exonuclease 7, which is XSEB, and finally C-terminal domain. So we mutated some parts of these domains and looked on the data that again the growth data that that are we able to have the function without any domains or not. So here's the data. So this data again is the same which I've already shown you, that when you have AccessCA encoded plasmid and you complement it, the cells are able to grow in the presence of ciprofloxacin. Now, what we have done is we have deleted and we have mutated the bit actually in the OB fold, which is the DNA binding domain. And you can clearly see that when we mutate the OB fold, then again there's a growth defect, which again which says that OB fold is very important for enzyme action. Again, we have mutated the catalytic part of the domains, so which is the R205A, and again you can see there's a growth defect with the catalytic domain as well. And finally, we have mutated the parts of coiled coils, which interacts with XSE-B, the smaller subunit of exonuclease 7. And you can clearly see when you mutate any of the part, again, there's a growth defect in both of them. So, what we found out that these all domains are responsible for the enzymatic action and are really important for XSE-A to repair the DNA. So now I've shown you the hypothesis that MARI activates the XSE-A gene and results in exonuclease 7. Also shown you that how this can repair the DNA, but I have not shown you visually that how this happens basically. So for doing that, I will show you some series of microscopic images, and in these images actually, all the cells have been grown in sub-inhibitory concentration of ciprofloxacin and also stained with Hush dye, which stains the DNA of the cells. Okay, so I'll show you the first part, which is wild type cells. So you can see here that the wild type cells are really small and have the blue color foci. The whole thing is intact, which is completely normal with bacteria. And they, when we delete or get rid of XSE-A from the genome, you can see that each cell actually becomes really elongated for some reason. And there's a chunks of the blue thing which you see, and which we think is the fragments of DNA across the whole profile, and which suggest actually that ciprofloxacin have resulted in DNA breaks in there, and the DNA is completely damaged. And so what we have done is we have used those complemented cells actually, where we are giving XSE-A cells back to the XSE-A gene back to the knockout in the presence of Marbox. And so the situation completely changes, and at least it starts to change. So when you have the Marbox intact and you're giving XSE-A gene back into the genome, so you can see the cells are again becoming normal like wild type, and even the DNA looks much better as compared to the XSE-A knockout. So now finally, we have mutated the Marbox, and they again did some complementation assay. So the final part, you can see that when we mutate the Marbox and they give the XSE-A gene back, it doesn't have any effect, which suggests actually Marbox is important for genetic complementation. And you can clearly see that the cells again become elongated like the XSE-A knockout, and even there's a lot of DNA damage in there. So I have shown you the visually and the microscopically. So now I'll show you my pulse field gel electrophoresis gel actually. So on this gel, you run really very long fragments on the gel, and to look over the sizes or the RNA or any DNA's activity or anything actually. So because there was a DNA damage, and we are running very long fragments on here, so we wanted to run it on pulse field gel electrophoresis. So you can see here when you run the wild type cells, and they are completely normal in the absence of ciprofloxacin. When you run knockout, XSE-A knockout, they are again behaving as normal. There's no damage at all. However, when you add ciprofloxacin to the wild type cells, there's a very little damage, which you can see even as a smear, a little smear, and even the dark bands here. So, but when you do a knockout with in the presence of ciprofloxacin, it damages the DNA. So you can see here, there's a lot of dark bands and even very dark smear here, which we know it's a DNA damage actually there. So now what we have complemented this actually with the empty PBR322 as a control. So again, you can see that it's completely same as the knockout cells, which means there's a DNA damage across the whole profile here. So next, what we did, we used the same PBR322 encoded AXA-CA gene, and they complemented it back. So you can see that they are becoming better, which means there's a DNA repair happening in these cells. And finally, we deleted the MAR box, and you can again see that there's again DNA damage over here, which means the MAR box is important. So far, I have shown you that how we measured the binding of MARE in terms like how did we found out the 33 new targets, and they highlighted some new targets like AXA-CA and MLAF, and there are many other targets which are responsible for multiple antibiotic resistance. And I have shown you that our gene actually AXA-CA, which is important for DNA repair. So when fluoroquinolones or quinolones or ciprofloxacin acts on the cells, they generate DNA break, and AXA-CA is able to repair them easily. Okay, so I've shown you a lot about AXA-CA. Finally, I'll tell you about a bit actually about MLA-FEDCB system. So this system is also targeted by MARE. So to explain it better, I'll show you the bacterial membranes first. So we know the bacterial membranes are asymmetric. So in order to maintain the barrier function, it has to be asymmetric. So what is the meaning of asymmetric is, so we have inner membrane, so inner part and the outer part of inner membrane is both composed of phospholipids, and the outer and the inner membrane is separated by periplasm. However, on the outer membrane, the inner part of the outer membrane is composed of phospholipids, but the outer part of the outer membrane is composed of lipopolysaccharides. So in order to maintain the barrier function so that none of the molecules or like antibiotic molecules doesn't come in, it has to maintain this membrane. So now our MLA-FEDCB system sits on the inner part of the membrane. So there can be two possibilities which we think actually might be happening with this particular system. So this MLA-FEDCB might be acting as an ABC transporter protein. So if it's acting as an ABC transporter protein, then we should see antibiotics, if they are present inside the cells, they can easily diffuse outside the cells through periplasm. However, if we delete any gene from this system, we shouldn't see antibiotics go outside the cell, and it will be properly functioning. So I'll show you the data later. But there's another possibility that together with MLA-A and MLA-C, it helps in maintaining the barrier function. How it helps in maintaining the barrier function? Because it maintains the phospholipids on the outer membrane by transferring the phospholipids from the outer membrane to the inner membrane. And so this in turn actually, this in turn maintains the barrier function. So if the antibiotics are trying to come in, they cannot. But if we mutate any of this bit actually, then we should see that there's a phospholipid accumulation. So now there's no asymmetry maintained and there's no barrier function. So if now the antibiotics are trying to come in, they can easily come in and they kill the cell. So if this is the case, then we should see that if we delete any of these genes actually, we should see accumulation of antibiotics inside the cell. So to test these possibilities, the first part of the possibility, which is ABC transporter, we did some efflux assay. So efflux assay is like if you give any particle to the cells, and if they are able to pump it out, we should see some activity on that. However, with wild type and any of the knockout of MLA system, we don't see any efflux because they both remains the same. So which rules out the possibility of it being a ABC transporter protein. Finally, what we have done an accumulation assay. So we have done a doxycycline accumulation assay, which is a type of tetracycline. And you can see here that the wild type cells are not able to accumulate the antibiotics. But if you delete any gene, when the barrier function is not maintained, then the antibiotics like doxycycline can go and accumulate inside the cells, which if you delete any system, the barrier function is not maintained and they can easily kill the cells. However, in the wild type situation, the barrier function is maintained, and hence you are not able to see the accumulation, and it's just because of the asymmetry which is maintained by the MLA in terms of MRA actually. So as a summary, here's the cell with its chromosome. This is the MARA system. It has got mutation in MARA gene, and because of that, they produce MARA, because MARA represses is not able to repress the system. And it targets, so when the drugs comes in, like quinolones basically comes in, it results in DNA breaks. MARA starts targeting XSCA, activates its function, and it's able to repair the DNA. Okay, so now the next part which I've explained you was MLA-FETCB. So this also is targeted by MARA and activated by MARA. And when this system activates by MARA, so if the antibiotics are trying to come inside the cells, they cannot, because it's maintaining the barrier function. And finally, I would like to just thank my boss and all of the members of the lab, but in particular, Laura Pittick's lab actually, who helped me a little actually in our experiments. And thank you very much. I'm happy to take any questions you might have.
Thank you, Pratik. Thank you so much. Is there any question? House is open for the questions. Thank you so much, Pratik. I think there is no question. Let's move towards our last speaker. It is Dr. Muhammad Yasir. Let me introduce you about Yasir. Yasir has completed his PhD by obtaining the Darwin Trust PhD studentship at the University of Birmingham, UK. He has been working on gene expression regulation in pathogenic bacteria to understand the regulation of genes involving pathogenicity in a pathogenic E. coli. He has been working on the development of understanding bacterial gene and promoters during his PhD. Nowadays, he's working at the Quantum Institute UK on a project involving the development and implementation of an advanced version of transposon-directed insertion site sequencing, TRADIS, which we have called TRADIS Express. TRADIS Express technology enables us to assay the whole bacterial genome in a certain stress condition down to sub-gene level resolution. Yasir is using TRADIS to study the bacteria into the food chain. I request Yasir to please start the talk. Yasir, can you hear me?
Yes, thank you very much, Fayaz, for generous introduction.
Thank you.
Good morning, good afternoon, everyone. So TRADIS Express, as Fayaz has mentioned, is a functional genomic tool to understand bacterial genomes. So in today's talk, we will be discussing what is the TRADIS Express method and what are its applications. So TRADIS Express, it stands for transposon directed insertion site sequencing with expression. So as we all know, transposons are the jumping genes, and we can make them jump onto any DNA, and in this case, bacteria. So when we make them jump onto the bacterial chromosome, they can be inserted into the gene or intergenic regions. If they insert in the gene, they inactivate that gene. And if they inactivate a gene and the bacteria still can grow as the gene A, so that gene is called non-essential gene, because the bacteria can survive without that gene. So in case of gene B, if they inactivate a gene and the bacteria cannot grow, that is called essential gene, because that gene was required for the life of bacteria. So we can make transposon mutants, about 100,000 to 1 million mutants, by transformations or conjugation method by making transposons to jump onto the bacterial chromosome and collecting those mutants. And then we can extract the DNA and we can sequence that. So instead of sequencing the whole genome, we sequence starting from the transposon and going into the chromosome. So we will find out the location of the insertion. So we then map the reads, and if the reads are mapping to the top strand, they are shown in this diagram with the red arrowheads. And if they're mapping to the bottom strand, they are shown in the blue arrowheads. So the number of the arrowheads are showing the number of the mutants we found in the community by the sequencing, and we can align multiple reads using the same principle. So we can show the insertion sites without arrowheads, like just lines. So each line's height is showing the number of the mutants, and the position of the line is showing where the insertion happened on the genome. We can show the insertions on the forward and the backward strand on the same side as well. So this is how the real TRADAS data looks like. So we can see that in the red boxes are showing these are the genes where no insertion has happened. So statistically, it's not possible that no insertion would have happened in these genes, because we made about 1 million mutants and there are only 5,000 genes, about 5,000 genes in E. coli. So statistically, it's not possible, but because whenever insertion happens in that particular gene, bacteria dies and they are absent from the population. So that way we know that these genes are essential for the bacteria to survive. So as we need different equipments to survive in different conditions, bacteria need different